Okay, so let's begin the first lecture of this training course, Design and Seismic Resistant RCC Building. Previously, we have done one demo class, and in that we saw what we were going to learn in this training course and some basics about the design philosophy, finite element analysis, design capacity versus design demand, and other various things. So we will start our first lecture, and our first lecture will be preliminary design of structural elements. In this preliminary design, we will perform some very simple design calculations of slab, beams, and columns. And these will be preliminary design, and the result of this design we get different cross section of column, beam, or slab. And the result of this design will be used as input when we model our structure in ETABS. So let me begin this presentation. So I prepared a simple plan for a residential building for which we are going to perform analysis and design. It is a 2.5 storied building, or you can say 3-story building. As you can see here we have ground floor plan. Let me just Here we have ground floor plan having an area of about 1207 square feet. Here we have first floor plan. The area is greater compared to ground floor. It is 1274 square feet, and second floor has an area of about 945 square feet. Here you can see staircase and different rooms: living room, kitchen room, master bedroom, common toilet, bathroom, and same is the case for first floor as well. And in the second floor we have this terrace. We have one big bedroom, common kitchen, common bathroom, and staircase. And these three will be the plan for our analysis and design. Here I have put the section of the building at YY. Let us see where is YY. This. Here is one plane through which we have cut, and we are going to see section of the building across this plane. So this will be the section of that building. We can see our floor height is 9 feet and 4 inch. 9 feet and 4 inch. Here is our opening schedule. This opening schedule might be necessary when we perform calculation for masonry load, because we may have to, or we can subtract the portion of doors and windows while calculating the load. And here I have drawn a beam layout plan of this building, the same building that we have seen in this presentation. These dimensions were in feet and inches, so I drew with my hand by converting those distances into units of meter, because we will be performing analysis in meters in ETABS. We can put units in feet and inches at that moment also, and the ETABS will directly convert them into meter, but for simplicity I have converted the distance, the units, into meters and drawn a general beam layout plan of building. So you can see in this horizontal axis we have two grids, 3.40 meter and 4.45 meter, and in the vertical axis we have 4 grids. So let's begin with the preliminary design of beam. Before conducting a preliminary design, we have to find the critical section for that frame element for which we are going to perform the preliminary design. So in the case of beam, what will be the critical beam? For which beam should we perform preliminary design? Our selection criteria is longest beam. We have to select the beam of longest span. So in the previous slide, if we look at this general beam layout, we can see that our longest beam will be that of 4.45 meters. The second longest will be 4.06, and other are in decreasing magnitude. So our longest beam will be this beam, whose length is 4.45 meter, and it lies between grid B and C. So our selection criteria will be longest beam, and the span of that beam is 4.45 meter or 4450 millimeter. So for preliminary design, we will design the beam using two criterion. One is the deflection criterion and another is based on ductility criterion is prescribed by code 13920. So first we derive the depth of beam using the deflection criterion, and that deflection criterion we use the simplified form of IS 456 2000 and this clause number 23.2.1. So IS 456 2000, as you know, is the design code for reinforced concrete structures, and in this clause of IS 456, if we look at the right hand side, I have posted a screenshot of that clause. The clause says the vertical deflection limit may generally be assumed to be satisfied provided that the span to depth ratios are not greater than the values obtained as below. So there are various cases, and the vertical deflection limit shall be satisfied if the limits imposed by these clauses A, B, C, D is not greater than the specified value. So based on these clauses, we have made a formula. Our formula will be span by effective depth. The ratio of span to effective depth is governed by these 5 values. BV means basic values, and these other MFT, MFC, MFF, and MFS are modification factors is proposed in this code. So what is our basic value? First, let us calculate basic value. Let's look at this 23.2.1 clause number A, basic values of span to effective depth ratios for spans up to 10 meter. The length of our beam is 4.45 meter, so it's okay. So basic values for cantilever beam is 7 meter, simply supported is 20 and continuous is 26. So the value of this basic value depends on end conditions. As we can see in our, let's go back to our layout. Our beam, wherever you look, in whichever grid you look, our beam is continuous at one end and discontinuous at the other end. So we don't have an exact value to be taken from here, so we take the average of simply supported 20 and continuous 26, because our beam is not continuous at both ends, but also it is not simply supported at both ends. So we shall take the average of these 20 and 26, which will come out to be 23, and that will be our basic value. Now this B, C, D, you can go to your code, go to this clause number and read in detail about this other clauses. For this, I will just look at how we can calculate MFT, MFC, MFF, and MFS, these 4 factors. So our MFT means the multiplying factor for tension steel. We derive this value from figure 4 of IS 456 2000. Immediately after that clause 23.2.1, which we talked about, there is a figure 4 which you can also see in the right hand side, and from this graph we will derive the value of MFT. For this case, for deriving the MFT value, let us suppose that the percentage of tension steel is 2.5%. This is just the preliminary design. So we know that for beam, you must have learned that the maximum reinforcement shall be 4% of cross-sectional area. But 4%, we won't be having so much of reinforcement in beam. So let us assume that we have 2.5% tension steel in beam. You can assume any value, because this is just the preliminary design. We are just choosing the sections. By using those sections, we are going to start the modeling in our ETABS. So we suppose that we have 2.5% tension steel, and if you draw a vertical line from 2.5, where is 2.4, 2.8 means this middle value will be 2.6. So the value between this middle line and this will be 2.5. I drew a vertical curve from this point to 2.5. I took this curve up to this fs equals to 240 curve, and from this point I drew a horizontal line. So my modification factor came out to be 0.8. So MFT will be 0.8. So another factor is MFC. For MFC, we will be looking at figure 5. For this, we looked at figure 4. For MFC, we looked at figure 5, and MFC means multiplying factor for compression steel. So we assume that we have 1% compression steel in our beam. Here it is, figure 5. We have 1% compression steel. We drew a vertical line up to this curve, and from this curve we drew a horizontal line. Our modification factor came out to be between 1.2 and 1.3. So we took our modification factor as 1.25. Our next modification factor shall be MFF. That is the reduction factor depending on wave width to flange ratio. For this, we have to look at IS 456-2000 figure 6, this adjacent figure, and we assume that our wave width to flange ratio is less than 0.3. So if we draw a vertical line from 0.3 to this graph, to this inclined line, and from there if we draw a horizontal line, we will get the reduction factor to be 0.8. So MFF will be 0.8. And finally, our fourth factor, besides basic value, there were 4 factors. Our fourth factor shall be multiplying factor for span of beam. Our span is less than 10 meter, which we have already seen when calculating the basic value. So we take factor as 1 for span less than 10 meter. So we have got the value of factors, all factors, 5 factors. So our formula, you can remember, was span by effective depth ratio equals to basic value into other 4 factors. We put the value of all these factors here and multiply those factors. We get span by effective depth ratio 18.4. So we have the span, we have this ratio, we can calculate D effective. D effective shall be span by 18.4. The span of our beam is 4450 millimeter divided by 18.4, so the depth of our beam will be 241.85 millimeter. This is the effective depth. After calculating effective depth, we can calculate total depth or overall depth. For that, we have to assume what diameter of rebar, what diameter of reinforcement is used in column. Generally, for a residential building, if we don't have any complex structure, I don't think we need more than 16 mm diameter bars. So let us assume that diameter of rebar is used in our beam is 16 mm. Our overall depth will be effective depth plus half the diameter of bar plus clear cover. So our effective depth is 241.85 mm. Half of bar is 8 mm, and clear cover, we have to put clear cover 25 mm. We get 274.85 mm. So let us assume the overall depth something greater than this value. We assume that our overall depth is 300 mm, that is 12 inches. So we got to the value of 300 mm depth from deflection criterion. Now we have a second criterion also, which is the ductile detailing criterion. And from this ductile detailing criterion, we get the minimum depth of the beam that we have to put. This minimum depth, we may get the value more than 300 mm also. If we get a greater value, then we have to put that greater value as the minimum depth. And for this minimum depth, or for this ductile detailing criterion, our design will be based, our preliminary design will be based on IS 13920 1993 code. Recently, I think in 2016 also, an updated version of this 13920 code has been drafted. If our preliminary design will be based on updated version, then I will mention this year as 2016. Otherwise, if 1993 and 2016 code do not have any differences, then I will mention 1993. So the spacing of hoops, this is written in this code, the spacing of hoops over a length of 2D at either end of a beam. shall be minimum of d effective by 4 and 8 times the diameter of the smallest longitudinal bar. This clause 6.3.5 says about this criteria. Let's look at here in right hand side. You can see I have posted a screenshot of that clause. What does it say? The spacing of hoops over a length of 2d, where d is the effective depth of the beam, at either end of a beam shall not exceed d by 4. Let me just draw something. So if this is our beam and if d is the effective depth, then the spacing of hoops over a length of 2d means, let us, this distance is 2d, this distance is 2d, and at the other end this distance is 2d. So at either end of the beam over a length of distance 2d, this distance will be 2d and this distance will be 2d. What will be the spacing of stirrups or hoops over this length at both ends of the beam? The spacing shall not exceed d by 4, that means effective depth by 4, and 8 times the diameter of the smallest longitudinal bar. However, it need not be less than 100 mm. So the spacing should not exceed d by 4 and 8 times the diameter of the smallest bar. So let us assume spacing is 75 mm. Let us assume the spacing of bars here is 75 mm. It's okay because the spacing also the spacing should not be less than, it need not be less than 100 mm. So we can put 75 mm. Let us assume, to avoid construction difficulties, we put spacing equals to 75 mm. So effective depth of the beam by 4 should be 75 mm, because in this clause we can see the spacing should be minimum of these two criteria, and one criteria is d effective by 4. So effective depth of the beam by 4 should be equal to 75 mm in the list, in the minimum. So effective depth of the beam then will be 4 into 75 equals to 300 mm. Then overall depth, look here, we have got effective depth of the beam in this case to be 300 mm. In the previous deflection criterion, we obtained total depth 300 mm. So here overall depth will be increased, also the effective depth have been increased. So again, overall depth of the beam will be the effective depth plus diameter of the bar to be used divided by 2 plus clear cover. If you add this, you get 333 mm. So we assume the depth to be a little greater than this. For simplicity, we assume 350 mm, that is 14 inch. And there is another clause in IS 13920 in 6.1.4 which says the depth d of the member shall preferably be not more than 1 by 4 of the clear span, because if the depth is greater, then that beam will act as a deep beam, and in deep beam compared to flexural character, the shearing forces, the shear deformation shall be predominant, and it has a different analysis process and different nature, a different behavior to forces. So we shall also ascertain that the depth d of the beam is not greater than 1 by 4 of the clear span. So if we put our ratio, clear span is 4450 and depth is 350, we get a ratio 12.71 which is greater than 4, so it's okay. So from these two criteria, we got the depth of beam to be 350 mm. Again, remember, this is just a preliminary design and the design value may change while actually modeling and analyzing the structure later. So now we have determined the depth of the beam. Now let us calculate, let us design in preliminary fashion for the width of the beam. So we have two clauses in IS 13920 code that says 6.1.3 says the width of the member shall not be less than 200 mm, and the member shall preferably have a width to depth ratio of more than 0.3 in 6.1.2. So minimum width shall be 200 mm let us take width of beam to be 230 mm. This passes this criteria, which is it should be it should be greater than 200 mm. And in second criteria, the ratio of width to depth 230 by 350, 0.66, which is greater than, this is not 3, this is 0.3. So this is 0.3. This 0.66 is greater than 0.3, hence okay. Both these criteria have passed. So finally, we will be beginning our structure with 350 mm depth beam and 230 mm width beam. This completes the preliminary design of beam. Now let's go to slab portion. If you want, you can contact, you can comment, and if you need, I will provide this lecture so that you can look by yourself the preliminary design process. I will also provide that AutoCAD plans of the building that we are going to analyze in the ETABS. So, design of critical slab. While performing design of beam, we took a critical beam. For that, we looked at the span of the beam and we did the preliminary design for the beam with the longest span. So, which is the critical slab? How do we select a critical slab for performing preliminary design? Let me go back to the first, that beam layout model, so we can see the critical slab. Look at this beam layout plan. So how do we say this was our critical beam or this was our critical beam? Let's suppose this is our critical beam. So which will be our critical slab? Our critical slab will always be adjacent to the critical beam. In this case, it's easy that our critical beam, okay, let's suppose that this is our critical beam because 4.45 meter length is the same. So our critical slab will always be adjacent to the critical beam. That means our critical slab can be this or this or this or this. So how do we select the critical slab among these four? So we have to look at the other span of the slab. We selected this beam because it has the longest span, 4.45 meter. All of this slab has one span is 4.45 meter. Now we have to look at the other span. This slab has 4.06 meter, this has 2.70 meter, this has 3.58 meter, and this has 2.34 meter. So critical slab is that slab for which the shorter span is the longest one. Did you understand what I mean to say? Let's look at this. For all of these four slabs, the longer span is the 4.45 meter. So we have to select that slab for which the other span, the shorter span, is the largest. 4.06 meter is the largest here as compared to these four. This is the largest span among the shorter span. So we select this slab as the critical slab. 4.45 meter and 4.06 meter. Okay, the selection criteria is slab having longest span among the shortest span of all slabs. That is what we did. Our longer span was 4450 meter, and to select the slab, we looked at the longest span among the shortest span. That will be 4060 mm. This will be our critical slab. Let us assume trial depth of slab is 125 mm. So this is the procedure that we follow for the preliminary design of slab. Our dead load intensity shall be the depth into the unit weight of concrete, 0.125 meter, which came from this depth, into 25, that is 3.125 kilonewton per meter square. Let us suppose our finishing load intensity is 1 kilonewton per meter square, and live load intensity. Live load intensity, if we look at this right hand side, we derived from IS 875 part 2 code. This is the code for live load to be imposed upon building, and it says that for residential buildings in table 1, imposed floor loads means live loads. For residential building in dwelling houses, for all rooms and kitchens, our uniformly distributed load in kilonewton per meter square shall be 2. So we took 2. So we have 3 load: dead load, finishing load, and live load. Let us calculate total design load by using a load factor of 1.5. 1.5 into sum of these 3 loads, we get 9.1875 kilonewton per meter square. After calculating the design load, we have to look for, you may remember that in your undergraduate courses you have learned the design of slabs by using different coefficients based on the condition of the slabs, based on the restraint condition of the slabs. For that moment coefficient calculation, we have to look at clause 24.4 and Annex D of code IS 456, that is the design reinforced concrete code. So first, what does 24.4 clause says? The slabs spanning in 2 directions at right angles and carrying uniformly distributed load may be designed by any acceptable theory or by using coefficients given in Annex D. So we'll be using this method, using those coefficients. And those coefficients I have put, those coefficients come from Annex D or table 26. I have selected the required coefficient and put in the diagram here. So what was the boundary condition of our slab? You can remember our slab was at the corner. It had 2 edges continuous, 2 adjacent edges continuous, and 2 adjacent edges discontinuous. So our slab boundary condition is 2 adjacent edges discontinuous, and I have selected the moments, sorry, I have selected those coefficients for the 2 adjacent edges continuous criteria, and I have put it here. Our aspect ratio means the ratio of longer span to shorter span is nearly equal to 1.1, which we will need here. Short span coefficients, to calculate short span coefficients and long span coefficient. Those are dependent upon values of Ly and Lx, Ly and Lx. So let us see what will be our short span coefficient. Our short span coefficient will be obtained from these 1, 2, 3, 4, 5, 6, 7, 8. We have 8 columns, and these columns means different values of short span coefficient for different values of Ly by Lx ratio: 1.0, 1.1, 1.22, 1.3, 1.4, 1.5, 1.75, and 2. Fortunately, our aspect ratio has come equal to 1.1, so we can directly take the value under this column 1.1. Suppose if it had come 1.05, then we would have to interpolate between these two values, and that will be another calculation to perform. But since our aspect ratio is 1.1, we can just take this. So short span coefficient, here let's look at this. For 2 adjacent edges discontinuous, we have different factors: moment coefficient for negative momented continuous edge and positive momented mid span. So our short span coefficient shall be for continuous edge. For continuous edge, for Ly by Lx 1.1, we have 0.053. I wrote minus here because we have a negative moment at the edges, but it won't matter here. I just put it minus for the sake of saying that this moment will be negative. For continuous edge, our factor will be 0.053, and for mid span 0.040. So these two will be short span coefficients, and this is represented as alpha x. And for long span coefficient alpha y, we have same values for all Ly by Lx ratios. That is, long span coefficient is independent of Ly by Lx ratios. Long span coefficient shall be minus 0.047 or 0.047 at the continuous edge, and for mid span we have 0.035. So these values we took from the table and we wrote it down based on the condition of our slab, based on the boundary condition of our slab. So let's go to another slide. Now, after calculating the load and selecting the moment coefficients, now we have to design the slab. And our first design is based on balance section criterion. You must have learned what do you mean by balance section in your RCC course in the first or second lesson. In the introductory lessons, you will learn about the behavior of beams or slab or column in flexure, and in that you will learn about under reinforced, over reinforced, and balance section. So for balance section criterion, we perform our calculations in this way. First, we calculate the critical moment coefficient for balance section criterion. What will be the critical moment coefficient? Let's go to the previous slide. That critical moment criterion shall be among these alpha x values, the largest of those values, irrespective of this sign. We will take the modulus of this 0.053 or 0.040 if it was there, and we will choose the largest coefficient value. If you can see, 0.053 is greater than 0.040. So our critical moment coefficient will be 0.053. Using this critical moment coefficient, we will calculate critical slab moment, which will be this alpha x value into total load, total design load that we calculated using design load factor and LXC square. So alpha x is 0.053, design load is 9.1875, and LXC square is the shorter span square, 4.05 square, we get 7.987, which is nearly equal to 8 kilonewton meter. So let us assume that we are using M20 grade of concrete and Fe 500 grade steel. So FCK, this characteristic strength of concrete shall be 20 MPa and yield strength of steel shall be 500 MPa. And for this, our depth of slab for balance section shall be 0.133 FCK BT square. FCK we will use 20, B we will use for unit width, 1 meter width, and D we shall calculate. So for depth of slab for balance section, we are going to use this equation. Remember, this factor 0.133 that we have used in this equation is for 500 grade steel. If it was 415 grade steel, this would be 0.138. If it was another grade steel, this would be another factor. This 0.133 factor will be for 500 grade steel, so remember that. So we have to determine the value of D from this equation. M value we put 8 kilonewton meter, B value we keep 1 meter, FCK value 20, and from this calculate D, we will get D is equal to 64 mm. So from balance section criterion, we got the value of D to be 64 mm. Another we have deflection criterion, and for deflection criterion, you have seen this clause 23.2.1 while designing for beam, while doing the preliminary design for beam. Based on this clause, we will calculate the depth of critical slab. So I will go a little bit faster here because we have already seen this clause. Based on this clause and based on this deflection criteria, we have span by effective depth ratio is equal to basic value into MFT. There were besides basic value, there are 4 other factors while designing beam, but here we won't have as many factors, we only have these 2 factors. So basic value will be 23, that is average of 20 and 26 as we did previously for one is discontinuous. Assume the depth of slab is 125 mm, so effective depth shall be 106 mm. So how this came out? We did overall depth is effective depth plus 5 by 2, that is the diameter of reinforcement divided by 2 plus clear cover. So our effective depth will be overall depth minus clear cover minus, if we assume that we use 8 mm dia bars in the slab, 8 by 2 is 4. So 125 minus 19 will be 106 mm. This will be the effective depth. So critical moment coefficient for deflection criteria is the maximum one at the mid span. What moment coefficient did we use for balance section criterion? We used Among these alpha x values, among these two values, we selected the modulus of the maximum one. Now for critical moment based on deflection criterion, because deflection of a slab will be greatest at the mid-span, we shall use the greater value of these two coefficients, 0.040 which is for mid-span and another 0.035 which is also for mid-span. Why are we looking at mid-span? Because deflection of the slab shall be greatest at the mid-span. So among these two values, the higher is the 0.040. So we use the same coefficient here, 0.040. And BV we have already written. So now critical slab moment shall be the same formula, but here alpha x will be 0.040. This is the design load and this is the LX. We get 6.03 kilonewton meter. So based on that moment, now how do we calculate the percentage of steel? For that, we will be looking at chart 16 of SP16. SP16 is the design aid for reinforced concrete. That chart 16 I have written here, I have presented here on the right hand side, which says chart 16 flexor singly reinforced section for Fy 500 Newton per mm square, that is 500 MPa, and FCK 20 MPa, which you are using in this design. So this chart has in this vertical axis, in this right hand side, we have moment in kilonewton meter. You may not see this because it's very small. On this left hand side, we have effective depth in centimeter, and on this horizontal axis, we have a reinforcement percentage. So we have two values. We have our effective depth, which we got 106 mm in the previous slide, and we have our moment. These curves are for the moment. We have two values, effective depth and moment, and we will calculate reinforcement percentage. So from this 106 mm, which is our effective depth, I drew a horizontal line up to that curve, which represents our moment of 6 kilonewton meter. If you look 6 kilonewton meter, this here 6 kilonewton meter curve is this. So I drew a horizontal line from this vertical axis of effective depth to this curve and then drew it downward to get the reinforcement percentage. This reinforcement percentage we nearly get 0.13 percentage. You can download this, or I can provide you this SP16 and go to chart 16 and also draw lines to see what I have done here. I drew a horizontal line from effective depth, this vertical axis, to that curve which represents our critical moment, 6 kilonewton meter, and from that curve I drew a vertical line to this reinforcement percentage axis, from which I got required reinforcement is AST equals to 0.13 percentage. Now let us compare this with from the AST that we get from formula. This AST formula is this. You must have learned about this formula also in your RCC course. From this we determine the percentage of reinforcement, which is AST by BD. This BD we take it to the left hand side and then perform those calculations, from which we get 0.127 percentage, almost equal to 0.13 percentage. So we know according to our code for high strength bars, the minimum AST, the minimum percentage of steel in slab is 0.12 percentage. So it's okay. These two values are greater than 0.12 percentage. We assume the percentage of steel to be 0.13 percentage. So this is not 13 percentage. I'm sorry, I made a mistake here. This is 0.13 percentage. So from deflection criterion, we got PT 0.13 percentage. Now let's come to calculate depth. For calculating depth, we again go to figure 4, which we saw during design of beam. In that, we assumed that the percentage of tensile reinforcement in beam is 2.5 percentage, and from that we derive the modification factor. But here we won't do so because we have already got percentage of steel to be 0.12 percentage. So to draw a curve on this graph, we first have to derive the value of Fs, because we get different values of modification factor for different values of this curve Fs. Fs is sorry, steady stress of service load. Here we have formula to find Fs. Fs is 0.58 into Fy into area of cross section of steel required divided by area of cross section of steel provided. So 0.58 into Fy is 500 MPa into our area of cross section steel required and provided is the same, that is 0.13%. So we get this 1. From this we get Fs equals to 290 megapascal. Now our percentage of tension reinforcement is 0.13. We draw a vertical line, we go up to this curve Fs equals to 290 curve, because we got that 290 curve, and from this curve we draw a horizontal line, and from this horizontal line this reaches up to 1.6. So our modification factor for tension reinforcement shall be 1.6. This is same that as we did in beam. So now our span by effective depth ratio is, we wrote BV, basic value, into MFT. This will be 23 into 1.6 equals to 36.8. We have the span of the slab. The shorter span is 4.05 meter or 4050 meter. So using this coefficient and this span of the slab, we derive the effective depth of the slab, which we get is 110.05 mm. So our overall depth shall be 110.15.4. Clear cover plus diameter by 2, which is 129.05 mm. While beginning this preliminary design, we assumed that the depth required will be 125 mm. We came a little greater than 129 mm. So now let us adopt overall depth of slab is 130 mm, and we will see what we can do during design. So our overall depth of slab came to be 130 mm. So we finished the design of slab. Now we come to the preliminary design of column. This is short one. Preliminary design of column does not have much calculation. I'm going to that grid. Okay, so we knew the criteria for longest beam and the critical slab. Now which will be the critical column? Critical column is that one for which the tributary load coming from all of its side is the largest. So if we see here, can we say that this is our critical column? Because if the load is coming from this column from all four sides, all four of this slab have their tributary areas which are contributing to the load on this column. If we see at this, the span of slab is greater in the adjacent slab for this column. So this is not the critical column because these two slabs are smaller. Although these two slabs are little bigger, but these two slabs are smaller. This slab is smaller as compared to this slab. So critical column shall be this column. So the selection criterion is the largest tributary area. For this we will go to 13920, the revised version, the updated 2016 version in clause 7.1.1, which says the minimum dimension of a column shall not be less than 20 times dB, where dB is the diameter of the largest diameter longitudinal bar in the beam or passing through or anchoring into the column at the joint. For now, let us suppose that the largest diameter of bar we will be using in our column is 16 mm dia bar. So according to this clause, and in B which says it should not be less than 300 mm also, we get 20 times 16. 20 times 16 is 320 mm. So the dimension of our column should not be less than 320 mm at least. We have to look at another criteria, which is the special confining reinforcement criteria. In the same code 13920/2016, which says in 8.1 B, have a spacing not more than, that is, the special confining reinforcement shall have a spacing not more than these three: 1/4 of minimum member dimension of beam or column, 6 times the diameter of the smallest longitudinal reinforcement bar, and 100 mm length. So if we look at this, the spacing of these stirrups or the spacing of these special confining reinforcements shall not be more than 1/4 of minimum member dimension of the beam or column. So what will be the maximum spacing of hoops or stirrups is per confining reinforcement? Maximum spacing of hoops shall be d/4. Also, that should not be less than 100 mm. So from this criteria, we get the minimum size of column, which will be this 4 times yes. If we assume minimum spacing is 100 according to this, then we will get the minimum size of column to be 400 mm. So we use, here we got 320 mm, but as we saw from the special confining reinforcement condition, that will not be sufficient. Our minimum size of column should be 400 mm, so we assume 400 mm by 400 mm column. I hope you understood this. This brings to the end of our presentation for the preliminary design of our main frame elements and slab element for beam, column, slab. We got some values. We got the depth of slab to be 130 mm. We got the dimension of beam to be 230 mm width and 350 mm depth. We got the dimension of column to be 400 mm by 400 mm. We will be starting our modeling using these dimensions that we obtained from the preliminary design and perform further calculations. So I hope you understood this lecture, this presentation. If needed, you can comment and I will be providing these slides. And in the next session, I think we will start with modeling in the ETABS. So this is the end of our presentation.